Hi all. So today we're going to talk about this problem 2.4, keeping a book up. So for part A, let's first draw a free body diagram here. So we have the normal force, which is the wall supporting the book. And then we also have gravity pointing downward. And we have the force F. And the small f represents friction. And so friction points upward here because we want to achieve minimum F, which means we want small f, friction, to help us as well. But as f gets bigger and bigger, the small f might actually point downward. And that's actually the problem for a later problem, which is 2.23, which I'll also cover later. So now let's focus on this problem first. Because this book is not moving, we know that the force in the x direction, the net force, should be 0, and so does the y direction. So let's try to list out these first. So the horizontal component of F, so this component here, this horizontal component here, it should be F cosine theta. And you have the normal force, which is opposite of this horizontal component, and therefore should be negative. So F cosine theta minus n equals to 0. And then let's look at the y direction. Let's define upwards to be positive. So we have small f, the friction, plus the vertical component of F, so this component here. So F plus F, capital F sine theta equals to g. And what is g? It's gravity. So it should be just mg. Or we can write it like minus mg equals to 0. And just to make things a bit neater, let's just write it as f cosine theta equals to n, f plus f sine theta equals to mg. And also there's another constraint we know is that friction is smaller or equals to mu n. So mu is the coefficient of friction. And basically we can solve for this system. So let's isolate f, friction, small f here. So small f equals to mg minus capital F sine theta. And so we know that mg minus capital F sine theta needs to be smaller or equals to mu n, which is f cosine theta. So it needs to be smaller or equals to mu f cosine theta. And let's isolate f since we're trying to solve for f. So mg is smaller or equals to mu f cosine theta plus f sine theta, which is equal to f mu cosine theta plus sine theta. And so we know that f is bigger or equals to mg over mu cosine theta plus sine theta. And so basically that is our answer to part A. Now, for part B, it is asking us for what theta is this minimum f the smallest? What is the corresponding minimum f? So this may be a bit confusing, but basically what it is asking is that, remember that we got an expression over f, which is like the lower bound of f. So it's basically asking us for what theta do we make this lower bound the lowest. So what is the lowest lower bound that we can get? Given at what value of theta is this lower bound the lowest? So basically right now this force is a function of theta. And since it is asking us for an extrema, so the minimum, we can do this by letting df d theta, so the derivative to be 0. So let's try to do that. So df d theta equals to d theta mg over mu cosine theta plus sine theta. And since mg is a constant, we can drag it out. So mg d theta. And I'm just going to write it in a negative power. So to the power of negative 1. And to find this derivative, we can do mg negative mu cosine theta plus sine theta to the power of negative 2. And now don't forget chain rule. So we need to find the derivative of this, which is negative mu sine theta plus cosine theta. And so now our expression becomes mg negative mu sine theta plus cosine theta over negative mu cosine theta plus sine theta squared. And now let's move this negative sign to the numerator. So we have mg cosine theta, mg mu sine theta minus cosine theta equals to mu cosine theta plus sine theta squared. So this is df d theta. And now let's let df d theta equal to 0. Since so the only way to make this expression 0 is by making the numerator 0. Since the book has a mass, which means mass is always bigger than 0, and we know that g, the acceleration, is never 0 either, we know that this part can't be 0. So the only way to make this 0 is if mu sine theta minus cosine theta equals to 0. And let's move cosine theta to the other side. We have mu equals to cotangent theta, which is basically cosine theta over sine theta. And now let's try to plug this expression back in. So we have the expression mg over mu cosine theta plus sine theta. So this bound is f needs to be bigger or equal to mg over mu cosine theta plus sine theta. And since we have the expression here, let's try to make this. So we can do this by dividing by sine theta. So mu cosine theta over sine theta plus 1. And then on top of it, since we're dividing by sine theta the denominator, so does the numerator. And so now we have f is bigger or equals to mu cotangent theta plus 1 over mg 1 over sine theta, which is cosecant theta. And so to find cosecant theta, let's recall the definition of these of trigonometry. So what is cotangent theta? Well, it is 1 over tangent theta. And what is tangent theta? Tangent theta is opposite over adjacent. So cotangent theta is adjacent over opposite. Let's draw a triangle. And we have right triangle theta here. That is called opposite, adjacent, and hypotenuse. I'm just gonna write HYP. Okay, so we know that mu equals to cotangent theta, which is 1 over tangent theta, which is adjacent over opposite. So we can also write mu as mu over 1. So we can let adjacent be mu and let the opposite be 1. And so what is the hypotenuse? Well, we can use the Pythagorean identity, which is square root of mu squared plus 1. And then what we're trying to do is we're trying to find cosecant theta. Cosecant theta is 1 over sine theta, which is hypotenuse over opposite. So it is basically square root mu squared plus 1 over 1, which is basically square root mu squared plus 1. And so now let's plug these in. So f is bigger or equals to mg square root mu squared plus 1. And since cotangent theta is mu, as we said here, it is mu times mu, which basically becomes mu squared plus 1. And then we can cancel a square root here because, well, mu squared plus 1 is basically square root mu squared plus 1 times square root mu squared plus 1, right? And mg square root mu squared plus 1 in the numerator. So you can cancel that out, one of them. So then we have f is bigger or equals to mg over square root of mu squared plus 1. And so that is the lowest lower bound that we found. 1 cotangent theta equals to mu. Or in other words, 1 theta equals to inverse cotangent of mu. So that's the minimum lower bound. For part C, the question is asking us, what is the limiting value of theta, below which there does not exist an f that keeps the book up? So let's think about it. What do we know? What are the conditions that f needs to satisfy? So what is f? Let's recall that. Well, f is the force that we use to push this book right upward. And so we know that this force must always be positive, right? Because if it's negative, that means you're pushing it, but to the left somehow, which is impossible. So let's think about it. 1 is this f, negative. Well, we know that mg should always be positive. And so for f to be negative, the denominator must be negative. And so the threshold value is when the denominator, mu cosine theta plus sine theta, is 0. And also when this denominator is 0, this right hand side becomes infinite as well, which is also impossible. And so we have this threshold value. So mu cosine theta equals to negative sine theta. And so mu equals to negative tangent theta, or let me write it, negative sine theta over cosine theta, which is negative tangent theta. And so only when tangent theta equals to negative mu, or we can write it as when theta is equal to inverse tangent of negative mu. So only when theta is this value, or smaller than this value, do we not have a possible f to hold this book up. And that is our answer to part C.